Well, last time we started talking about solving separable differential equations. We are going to look at two more examples in this session. This time we are going to be solving initial value problems. Our first example is y prime plus xy equals 0, and when x is 0, y equals e. You really want to write the derivative in terms of differentials, no matter how they give it. You want to write the equation in the form d of the function over dx equals the product. So in this case, we can do that by taking the term xy to the right-hand side, and thus writing the equation as dy over dx equals negative xy. If I just cross multiply, I get dy equals negative xy dx. I want to get the y to the left-hand side, so all I need to do is divide by y. I cross multiply first and then divide by y. I get dy over y equals negative x dx. Now the x's and y's are separated, so I can integrate. An antiderivative of dy over y is ln of absolute value of y. An antiderivative for negative x dx is negative x squared over 2. It's enough to put the constant of integration on one side, so I just put a c on the right-hand side. Next, we want to solve for c by using the given initial value. When x is 0, y is e. Plug those in here. Ln of absolute value of e is just ln of e, and that's 1. On the right-hand side, I have negative 0 squared over 2 plus c, which is just c. So c is equal to 1. I'm going to plug this back in the previous step, which gives me ln of absolute value of y equals negative x squared over 2 plus 1. If I want to solve for y, I need to get rid of ln first. So I take exponentials of both sides. I'm also going to simplify the right-hand side a little bit, just to clean up the look of the solution. If I take exponentials, I will get the exponential of the quantity negative x squared plus 2 over 2. This is the absolute value of y, so y can either be that exponential itself or it's negative. Because the function must be continuous, after all it is differentiable according to this, and it never takes the value 0 because it's an exponential, it must always be positive or always be negative. But since y is positive and x is 0, it must always be positive. So we really don't need to worry about the absolute value, which means y is just the exponential. Sometimes you might have to do a little bit of algebra to factor the right-hand side. It might either be just high school factorization, or you might have to use properties of exponentials and logarithms sometimes. As in the next example, y prime equals e to the power x minus y. When x is 0, y is 1. So I need to write e to the power x minus y as a product in order for method of separation to work. Of course, I write y prime as dy over dx. By properties of exponentials, e to the power x minus y is e to the power x over e to the power y. Now cross multiply. That separates the variables. Integrate each side. Again, it's enough to put the constant of integration on just the x side. So an antiderivative for e to the y dy is e to the y. For e to the x dx, it's e to the x. Then I'll put the plus c on the right-hand side. When x is 0, y is 1, so we can find the constant of integration by plugging those numbers in. I get e to the 1 equals e to the 0 plus c. E to the 0 is 1, so the equation says e equals 1 plus c. So c is e minus 1. Put this back in the previous step. Plug this in here for c. We get e to the y equals e to the x plus e minus 1. If I want to solve for y, I need to take logarithm of the left-hand side, logarithm to the base e or ln. So I get y equals ln of e to the x plus e minus 1.